I'll start by briefly introducing myself. So I'm Michelle Valente. I'm an application engineer at MathWorks for almost a year now. There's a small background. I did a PhD in robotics where I worked developing localization algorithms for self-driving cars. Then I worked for a while as a research engineer in the robotics field. And for a year now, I've been working at MathWorks, dealing with customers that use our robotic tools, but also computer vision, image processing, and deep learning. So today I will be presenting the seminar on how to develop autonomous systems with MATLAB and Simulink. First, I would like to start by just giving you a small introduction to what are autonomous systems. They are also known as robots. These robots are intelligent machines that are capable of performing tasks in their world by themselves without any or almost any explicit human control. There are several types of autonomous robots. It can be self-driving vehicles, mobile robots, humanoid robots, drones, and even these robotic arms. We can find these robots in a variety of fields, from medical applications to military, and even nowadays at our homes, like the small robots that clean our apartments. I would like to start also the presentation with a small example, just to illustrate the different types of autonomous systems that we can find in an industry application. So let's think about the smart autonomous package delivery. This is a classical example that shows how the market is growing towards what we're going to call the Industry 4.0, where we'll be able to see probably soon what we call a fully autonomous delivery chain. There are several stages in the delivery chain. We could imagine one that is how to transport products from the manufacturer to a warehouse. And we could think that in this stage, some autonomous level of automation level could be applied. For example, self-driving vehicles that would bring the products from the manufacturers to the warehouse, like self-driving trucks. Once these products arrive to the warehouse, some robots could be used, autonomous robots, to bring the products to their storage and just keep where they are supposed to be until the customer is going to buy the product. And we have the last phase that we call the last mile delivery that could be done, for example, by drones. My objective by showing this example is to show how there are different types of autonomous systems and how they can have very different types of requirements. For example, a self-driving truck needs to know how to make algorithms in a quite complex, dynamic environment, while robots in a warehouse needs to have very well optimized trajectory planning and control. And drones in the last mile delivery need to have a very different type of control too, to be able to fly between obstacles like the buildings we see here in the scene. Even though all the systems, they have very different type of requirements, they all follow kind of the same workflow for development. And that's what we're going to be talking about in this seminar. So what's the agenda for today? First, we will talk about what is this workflow for the development of autonomous system, and more particularly, how we can use MATLAB and Simulink capabilities to design, simulate, test, and then deploy solutions for all the different phases of this workflow. So this workflow starts with the modeling and the simulation of the systems. It can be modeling the entire system, but also how it interacts to the environment. Then we're going to gather the information from different sensors and apply sensor fusion algorithms and perception to perceive the environment. The next phase, we also have some localization and mapping algorithms. These algorithms are necessary for autonomous systems to understand the environment and to know where the system is located inside this environment. Once we have this information, we can actually start to plan our tasks, so have some steps of path planning and then control the robot. We also talk by the end of the presentation about the deployment and the connectivity to ROS environment. I have some echo, I don't know if there is some, okay, I think it's gone. Okay, so coming back, and as you can see, there are a lot of topics that we're going to cover in this seminar. Of course, I cannot go into a lot of details of each one of them, but the goal here is to give you an overview of what are the capabilities, the functionalities of MATLAB and Simulink to all these different stages of the development of an autonomous system. In order to present this stage, I separated them into blocks, the functional blocks of an autonomous systems, and then we're going to go over each one of these blocks. These blocks help us understand the different components of the system, but also the technology that is needed to build an entire autonomous system. So we're going to start by how to design the platform, and then we're going to add all the autonomous algorithms into this. So include sensing, perception, planning, and control, and then how to connect to external device and deploy the target. Throughout the presentation, we're going to have this chain here on the left that's going to let us see which part of the workflow we are talking right now. So let's start with the platform. So the platform, the idea is where we're going to model our system, and there are different levels of modelization that can be done. I separated this presentation of how to model platform and environment in 3 types of modelization. First, what we call the high fidelity robot modelization, which is going to include the kinematics, the dynamics, even the contact force of the system, or the mechanics aspect of the system. This is generally done through our plant modeling tool, such as Simscape. So this is a high fidelity level of modelization, but there are also some algorithms for the modelization of the kinematics of the system that can be used. These are out-of-the-box algorithms that comes with different toolbox, like the robotics system toolbox and the UAV toolbox. And another level of modelization is the environment. So if your application or robotic application interacts with the environment, usually you need to also model how this interaction is going to happen and test different types of scenarios. There are several tools that can be used for this modelization. We're going to talk about some of them here too. So let's start about talking about the plant modeling tool, Simscape. So Simscape, it's a tool that enables us to rapidly create models of physical systems inside the Simulink environment. And one of the blocks of Simscape, it's called Simscape Multibody. And Simscape Multibody provides a multibody simulation environment for all the 3D mechanical systems. It can be robots, vehicles, construction equipment, even aircrafts. So we can, for example, import CAD assembly models of the robotic system, which is going to include all the masses, inertias, joints, constraints, and 3D geometry into our model inside Simscape. We can also create our own model with the blocks that are already available in Simscape. That's going to represent, for example, the body parts, the joints that we're going to connect to the body parts, all the different constraints, force elements, and sensors. We can even create our own blocks using what's called a Simscape language that is kind of based on MATLAB. Like that, we can create high fidelity models of the physical system. And also Simscape is going to formulate and solve the equations of the motion of the complete mechanical system. And in the end, we're going to generate a 3D animation that can let us visualize the entire dynamics of the system. This type of simulation is quite useful when we want to refine the requirements of a mechanical system or, for example, optimize a system level performance. A small example just to illustrate how Simscape can be used. Here, it's an example where we're going to have a robotic arm and we're going to explore with simulation how are the different requirements of the motors. So by doing different trajectories, analyze what are the requirements for modeling the motor and actually do what we call actor sizing. So we can plot different types of information and analyze this type of information through the simulation in Simscape. So this is a small introduction to Simscape. Of course, there is a lot more information, a lot more details I cannot cover everything here today, but by the end of this presentation, I will leave some links of different types of trainings and videos that can help you go into more details of each one of the points that I'll be presenting here today. The next level of modelization that I would like to mention is the kinematics and motion modelization. There are different models that are already available with, for example, the robotics system toolbox, which has out-of-the-box tools to modelize the motion of a system. For example, we can define a simple type of simulation, as we see here in the scene, to test different types of motion models for mobile robots. It can be a bicycle model, a differential drive kinematic model, for example, Archimedes kinematic model. This for mobile robots, but there are also motion models available for example, robotic arms, such as the joint space motion model or the task space motion model. This is quite a simple way to add the motion model to our system. Usually this is used in a phase where we don't want to go into the details yet of this point. We just want to use a motion model maybe to test other parts of the algorithm. It can be the path planning, the perception, etc. Now let's talk about the last part of the modelization, the environment simulation, how to test the platform inside an environment. We can leverage different types of fidelity simulation environments. It can come from the most simple ones that we call the cuboid ones, because we're going to use kind of similar cubes to just create a simple type of scene to simulate cars or mobile robots, drones, etc. This is a very rapid scenario simulation. We can create different variations of it to test different parts of our scene. Or there is a more complex, more photorealistic type of simulation that's going to use an outside tool for this. It can be Unreal Engine, or it can be also other types of simulators like Gazebo, for example. In this part of the presentation, I will present specifically how we can also connect MATLAB and Simulink to the Unreal Engine. But first, let's see how it works for this cuboid fast type of simulation. There are different objects, functions that are available in MATLAB that let us create in a few lines of code, very simple simulations like we see here. For example, in the left for a mobile robot that's going to move from a point A to a point B. We can imagine that this could be very useful if you want to just explore different types of path planning algorithms. On the right, a type of simulation for drones, where we can also simulate the perception with the LiDAR sensor or the path planning algorithms, the control, etc. And just to show how it's not complex to do this with the code of MATLAB. So here it's how it looks like to create this type of robotic scenario. We create this object of the type robot scenario, and then we can just add information into it. For example, if you want to add static information, we're going to call this function called add mesh, that we're going to say the type of mesh we want. It can be a plane, for adding, for example, the gray plane here, or a box to add in the middle, the position, the color, different parameters. Then we can load a robot into it. Here we call this load robot function that let us load some model of robots that are already available, or we can even load our own model, for example, in a URDEV file, SDF file, or even a model that's coming from Cscape, for example. Then we can connect the model that we just loaded into the scenario, so transforming it into a robot platform. And then we can even add sensors to it, for example, an ENS, or we could add a LiDAR, for example. Then we can just visualize it or create, for example, a loop where we're going to run each step of the simulation and perform different tasks. So this is a simple way of creating, just with a few lines of code, a simulation that allows us to test and modelize different parts of our system. There are also some applications, some apps that facilitate this creation of scenarios. One example for automated driving simulation is the Driving Scenario Designer. This app is part of the Automated Driving System Toolbox, where we can add or ego vehicle with different sensors on it, radars, camera, lidars, and then create scenarios like we see here in the video, which we can, for example, add other cars around, create a trajectory, or even connect to a Simulink model that's going to control these cars around in the scenario. These are two examples of how to create quickly a very simple type of simulations with the cuboid word. But like I mentioned before, we can also create photorealistic simulation. This step is usually important when we want to test our perception algorithms that depend on a realistic scene. And these examples that I show here, they are using the Unreal game engine. So it's a video game engine that we can connect to directly from MATLAB and Simulink for simulations like the ones we see here. And there is a direct interface between Simulink and Unreal Engine. So there are some blocks available in Simulink that facilitate this interface. For example, this first block here that I'm showing, it's what we call the simulation 3D scene. Is the 3D scene configuration. So there we're going to have several parameters like what 3D word are we using. We can even define where is the light look, how is the light, how is the weather. And it's going to be really the parameters of the scene that we're simulating, the 3D scene. Then inside the Simulink model, we can add our actors, for example, the vehicle with the different poses that it's going to do, and connect sensors to it. There are different types of sensors available that we can connect to it. For example, if we go to the Simulink library, you're going to find the 3D cameras. The IDEO means the IDEO classic pinhole model, where we can also extract other types of information if you want. For example, depth and semantic segmentation. Also, we can simulate a fisheye camera that's going to have wide angles, or 3D laser scanners, 2D laser scanners, and radars. The idea is that inside these blocks, we're going to be able to enter several parameters that let us personalize each one of these sensors and make them close to the ones we are trying to simulate in real life. So here I showed how to interact to a 3D world like Unreal. We also have a tool that lets us create our own 3D scenes, because we can use some of the 3D scenes that are already available when we come with Unreal and Simulink. But when we are talking about simulation, sometimes we need to create our own scenes and specific variations that we want to test in our systems. And there is a tool that is called Roadrunner that was added to MathWorks quite recently in 2020 that allows the creation of 3D scenes that can be then imported to external simulators like Unreal, and then used, or for example, Carla, and then used with MATLAB and Simulink. I'll show this just a small video to give you an idea how this tool looks like. We can, the idea is that it's an interactive tool that lets us, quite in a simple way, create road environments and really personalize in details these road environments, like the marking on the ground, the elevation. We can even add a pedestrian's walk, change the types of marking on the ground, or add different type of textures to make it very realistic, as we see here. We can also add different types of props, 3D models to the scene. Like we see, we can use the ones that are already available or even import our own 3D models to it. The idea is to customize your own 3D scene and test different types of scenes for your autonomous system. After you create this 3D scene, you can then export it to Unreal and test all your algorithms of perception, for example. There is a new tool that was added to Roadrunner in the last release, the 22A release, that's called Roadrunner Scenario. So this tool let us now, instead of just create the automatic, not the dynamic, but the static information of the scene, but also the dynamic start of it. We can add vehicles, add some logic to it, and then simulate them. So we just change my pointer. Just a second. We can launch this. So for example, here we can add an ambulance, change the speed according to different conditions, then add another car that's going to change the lane and match, for example, the speed of the ambulance once it changes the lane. And then we can launch this simulation and see what it looks like. The idea is that this scenario can then be exported and in a common format for creating different driving scenario that is called open scenario, or even this can be communicated to MATLAB and Simulink to create different variations of behaviors of the vehicle. Once again, I cannot go into much details of this tool, but this is a quite recent tool that is very interesting if you're working with autonomous driving. So here, it's an overview what I presented for the modelization of the platform and the environment. There are several levels of modelization that can be done. The important thing to know is that with MathWorks tools, all these different levels of modelizations, they are easily we can easily communicate between these different levels. So we can, for example, move from one level quite easily inside the same environment. And most important, probably different teams that work with you work with different levels of modelization. So these teams can communicate between them when you're using the same environment of MathWorks with MATLAB, Simulink, and maybe other tools like Unreal and Roadrunner. Now let's move to the second phase of this workflow, the sense. So by sensing, I mean gathering information from different sensors. With MathWorks tool, we support a variety of common sensors that are used for autonomous systems, like laser scanners, cameras, variety of types of cameras, sonar, radars. We can connect directly for these sensors and stream this data directly in MATLAB and Simulink, or just use data sets and then test our algorithms with it. And then with different toolboxes, like the image processing toolbox, LiDAR toolbox, radar toolbox, we can apply image processing algorithms, data processing algorithms in general. That's going to prepare all this data for our perception algorithms later. For example, an image from a camera, usually before we apply some perception algorithms for object detection, we need to prepare this image. For example, correct the lighting of the scene. So these two boxes can be used to do all these data processing methods. There are also some apps that can be used to facilitate this stage of sensing. One very commonly used for autonomous systems is the camera calibration app. So camera calibration is the process of estimating camera parameters by using images that contain a common calibration pattern, like the one we see here in this image. Usually it's this type of chessboards. And the goal is to, by this app, we can load several images that were taken from the camera that points to this chessboard pattern. We know the characteristics of this chessboard, so we know the size of the squares, for example. And when we launch the calibrator, it's going to automatically detect the different points in this chessboard. The goal is that the algorithm is going to have an optimization to estimate the camera intrinsics, the distortion, and the camera extrinsics. These camera parameters, they're very useful to then remove, for example, the distortion of the lens, or measure objects, or reconstruct 3D scenes using multiple cameras. So in the end, we can analyze the error of calibration and export this to a variable or a file in MATLAB. This step of calibration can also be done between LiDAR and camera. So it's quite of a similar approach. I don't know why the video is not playing, but the idea is the same, that we're going to load a set of images, but also a set of point clouds that's going to observe the same type of board. And when we extract the chessboard corners and planes from the LiDAR and camera data, we can establish a geometric relationship between their coordinate systems to perform calibration. So the calibration of these two sensors means finding the rotation and translation between them. Why is that useful? It's because, well, LiDARs and cameras, they are commonly used together in autonomous systems because LiDARs have a quite of a precise information of the 3D spatial information, while camera has all this information about color and texture in 2D space. So really, we can use them to perform a better perception of the system. There are some algorithms that are already available in MATLAB that makes this fusion easier. For example, by just calling the function fuse camera to LiDAR, we can take all the information of the color of the pixels in the cameras and then add this information to the point cloud of a LiDAR. So we just need to pass as input the image, the point cloud, the calibration of the camera, which is the intrinsics, and the extrinsic calibration between the camera and the LiDAR. And the output is going to be like this point cloud we see here in the right that has the colors of each pixel that are really correspondent to a 3D pixel of the point cloud. Another way of using this calibration is for depth estimation for 3D reconstruction. So for example, if we have two cameras that are looking at the same scene, we can create a stereo system that's going to give us a 3D information of each pixel, an X, Y, Z points for each pixels of the two images. Before I move to the perception part, do you have any questions? Because I know it's a lot of information, so it might be good to break the questions into some points. Let me see if I open Teams. Any questions so far?
On chat, I don't see any question, Michelle.
Okay.
You can continue. Thank you.
Sure. So let's move to the third step of this workflow, which is the perception. Perception involves a lot of different types of algorithms when it comes to autonomous system. So it can be for detection of different things in the environment. It can be when it comes to automated driving, it can be detection of vehicles, pedestrians, or when it comes to industrial robots, it can be, for example, detecting an object that you want to do a pick and place type of task. Then once you detect these objects, usually you need to track them over time. So there we have all the algorithms of tracking. We're going to try to estimate the pose and the state of these objects over time. And then all these algorithms of localization and mapping, which is trying to estimate where the system is located inside an environment and while simultaneously creating a map of the environment. Let's start by the detection algorithms. Why my videos are not being played? Just a second. Just relaunch it. Okay. So for the detection algorithms, we can use one sensor at a time. For example, for object detection, we can use cameras to detect like vehicles, like I said before. Here in this example, we are using the deep learning method, the YOLO V4, which is a quite classic deep learning method for detecting objects in general. This is a model that was already trained to detect vehicles that is already available in your documentation. But we can also use this model to retrain to any object detection that you would like to do. So you can just perform a transfer learning we have some documentation that shows how to perform transfer learning using these models, but you create your own data set. It doesn't need to be that big because this model was already trained to different types of objects, and then you can retrain it for your own data set. And in the right, we have another example of how to perform perception using one sensor. In this case, we are performing a semantic segmentation, which means for each point of the data, in this case, it's a point cloud, we're going to estimate a class. So for example, we're going to estimate in purple, where is the ground, in green, the vegetation, in yellow, the vehicles. The same type of algorithms that also exist for cameras to perform semantic segmentation. In these two examples, we use one sensor at a time, but we can also and usually use more than one sensor for perception. Here is an example from the documentation of MATLAB, where the goal is to not only detect the vehicles using the camera, but we want to also estimate the distance between the car and the other vehicles. So for that, we're gonna use the camera with a deep learning model that was already trained and worked quite well to detect vehicles. And then we're gonna just transform this bounding box from the 2D images to the 3D point cloud of a laser scanner. The laser scanner gives us a good estimation of the distance to the object, so we can just get this information directly from the laser scanner. So here is how it looks like in just a few lines of codes, how we can do that. So let's say we have already our LiDAR point cloud. The first thing we do some pre-processing. So for example, we can remove the ground plane. Usually it's an important step for LiDAR when we will detect just obstacles, the objects that are over the plane. Then if there is a detection in the image, we're gonna transform the bounding box of the camera image to the LiDAR frame. For this, there is already this function, bounding box camera to LiDAR, that is available in MATLAB, that all we need to pass is the bounding box detected by the image, the point cloud of the LiDAR, and the calibration of the camera, and the calibration of the camera with the LiDAR. So the output is going to be this LiDAR bounding box that we see here. Then we can just create a function that is created in this documentation to compute the distance according to this bounding box, which is basically just finding the closest point of this bounding box and then seeing what's the distance according to the sensor. Then this information is going to be added to the image as we see here. We're going to show where it was detected with the distance of 24 meters. So here's an example of how to perform object detection and also fuse the information with other sensors. There are several types of applications, examples in the MATLAB documentation for deep learning user case. So perception is not all about deep learning, but since this is quite commonly used nowadays in autonomous system, I kind of focus this part of perception in these methods. And in our documentation, we have examples that apply for different types of applications. It can be for image processing, computer vision, where we're going to detect semantic segmentation, object detection, and even for LiDAR point clouds. When it comes to use deep learning methods, we usually cannot just use the out-of-the-box model that is already trained. If we want to retrain it for our own model, for our own data set, we need to perform what we call labeling and annotation of our data set. There are different tools that facilitate this labeling in MATLAB, depending on the type of data that you have. For example, for images, we have the image labeler, and for LiDAR, we have the LiDAR labeler. There is also one tool that's called the ground truth labeler that is quite useful for autonomous systems because the idea is to bring different types of data from different sensors into the same labeling tool. So for example, let's see the steps here. First, we would open this application and give as input different type of data. It can be images and point clouds. We can observe them in a synchronized way. For example, the image here and the point cloud, as we are seeing. Then, if we want to label this data, we can start by doing this in an interactive way. So here in the left, we have the labels that we are defining. So for example, we can define a main class that is vehicle, a subclass that is car. You could have another subclass like truck, for example, and even another subclass that's called tail light. Then we click on the label we want to create, for example, here tail light, and then click on the image to labelize it. The same thing we can do at the same timestamp using the laser scanner. So for example, if we want to label the car, we click on the car and just create, in this time, a cuboid label, that's going to be in 3D, to labelize this data. As you can imagine, it can take a long time if you're going to create this type of labels at each timestamp. So there are some automation algorithms that can be used to facilitate this labeling. There are some algorithms that are already available inside the app. So some algorithms are based on models that were trained to detect a specific type of objects. For example, the vehicle detector or the people detector that's going to automatically detect vehicles and people into images. And so there are also some methods that are trackers or interpolators. The idea of these methods is to help you not to have to label at every timestamp, but just in a few of them. For example, if we choose the temporal interpolator, we can just automate it by labeling the first frame of the image and then the last one. And if we launch the automation algorithm, it's going to automatically label between the first and the last frame using interpolation algorithm. There is also a similar interpolation algorithm for the point cloud. Same idea, we label the first point cloud, we label the last one, and when we launch it, it's going to automatically label the car between these different frames. These are the algorithms that are already available in the app, but you can also create your own algorithm. You can just call a MATLAB script from the automation tool there, and you can use any type of algorithm you want. If you already have a deep learning model that was trained with a specific type of data set, you can launch it, have a first estimation of the labeling, and then maybe just correct some of the false estimation by hand, or even create an algorithm that's going to connect different sensors so you don't need to label them separately. The idea is that in the end, once your data set is labeled, you can export it. So by clicking on the export labels, you can create a file with the data set or just export to a variable in the MATLAB Simulink workspace. You create a ground truth that's just going to store all the data and also the labels that were created. The traditional workflow, then when we are creating an AI model, it's going to be, of course, getting data, label them, and use this label to train a data set. But as we mentioned before during the simulation, we can also create automatically labeled data from the simulation algorithms, on the simulation external simulators. So for example, on Rio, we saw that the camera that we connect, we can also get the information from the semantic information from it. And so we can imagine this type of information could also be used to retrain or to train your AI model. And to finalize this part of perception and AI, just want to mention that AI is often part of a more complex system, usually this type of system that we're talking about, the autonomous robotic systems. And usually we use different tools for modeling, but also Simulink. And it's important to note that these AI models can also be imported inside Simulink. So in the Simulink library browser, we have a different type of blocks that let you import the different types of deep learning and machine learning models inside an entire Simulink model. So we can imagine that we can connect different parts of the algorithms, the perception part to the path planning, and then use, for example, a deep learning model there in the middle. So I talked about detection. Now let's move to another type of the perception algorithms, the tracking. So tracking, it's an essential phase for all type of guidance, navigation, control of autonomous systems. There are several trackers that are available in the MATLAB documentation. They're from the classic GNN to GPDA, PhD. I'm not going to go into details of all of them, but the idea is that the job of a tracker is to estimate the number of objects and their states, as for example, position, velocity, dimensions, using sensor measurements of one or several types of sensors. And these algorithms that are available, they have different types of parameters, of course, that can be changed, different types of filters, data association algorithms that can be plugged into it to personalize your own algorithm. I would like just to show an example to illustrate how these algorithms of tracking can be used. In this example, we're gonna fuse the detections from a 3D LiDAR with the detection of 2D LiDAR to improve the detection of vehicles in a highway. So the first thing is to create the scenario if we want to test it. So there I'm using one of the tools that I mentioned during the first part of this presentation, the driving scenario designer. So I created my scene. I added the ego vehicle with the two sensors that I wanted, the LiDAR and the radars. I added the other actors around, and then I launched the simulation. This is the kind of output I would get. So in green, we have the point clouds of the laser scanners. In blue, we have the radars. And we want to fuse this information to track these vehicles the 4 vehicles that we see here in the scene. The first thing is to detect these vehicles with the LiDAR. So LiDARs, they have as output point cloud. This is a 360 degrees coverage LiDAR. And the first thing to do, like we already saw in the previous example, is to remove the ground because we want to detect just the vehicles. So we can call a MATLAB function for that. And then also detect the bounding box of the different objects that we see in the scene. For this, we can use a clustering algorithm to detect the points that are forming a bounding box. Here below, we can see the bounding box covering all the points that are falling around this vehicle. Then we're going to connect a tracking algorithm that is going to track this bounding box over time. In this case here, we are using a joint probabilistic data association algorithm, the GPDA algorithm, which is a multi-object tracker. So it's going to track multiple objects at the same time. And we also use, just as an information, an EMM model. It's an interacting multiple model tracking filter, which is useful when it comes to vehicles because it gives the ability to handle all the maneuvering vehicles that change lanes. So when we add this tracker, the output is going to be the tracks as we see here for each of the vehicles. And we can observe that most of the time it works quite well. However, when a car comes very close to the vehicle, it might add some noise, like I think over here we see. So we see that L4, there was some confusion between the L4 and L3. The algorithm was not able to track it correctly because there were not a lot of points also from the LiDAR in the L4. That's why we're going to improve this detection using another sensor like the radar. So for the radar, we're going to use another type of tracking algorithm. In this case, we're going to use what we call an extended object tracker because we're not going to track a bounding box over time. We're going to track a group of points over time. The radar detections, as you can see, there are these points that are detected in blue here. And the tracks we can see as R1, R2, R3, R4 here. It's not necessarily more precise than LiDAR because the radar is way more sparse, but radar points can be more stable and give us also an estimation of the velocity of the cars. So let's look like how it's going to look like when we fuse these two types of tracking. So here, when we design a track level fusion, so we're going to perform the fusion in a track level. We're going to fuse the different types of tracks. We can see that the fusion, which is the F2, it's way more stable even when a car is passing near the vehicle. So we're able to stabilize this tracking and visualize it using multiple sensors. To finalize this example, there are also some metrics that can be used to analyze the quality of your tracking algorithm. It can be the missed targets, the false tracks. Also, there are some type of algorithms that give us a value of metric, like the GOSPA, for example. This type of metric, as lower it is, it means the tracker is the best. So we can see that most of the time, the LiDAR is better than the radar. However, sometimes the radar is better, probably when the vehicles are close to each other. However, through all the simulation, the fused results were more precise. So here go an example of how to perform tracking In this example, we were applying to automated driving, but tracking can really be applied to any autonomous system that has dynamic objects, dynamic actors around it. Now let's move to the last stage of the perception, is localization and mapping. So localizing an autonomous system usually means estimating its pose, which is composed of a position, X, Y, Z, and also an orientation. There are different types of algorithms for localization. It can be filter-based fusion algorithms, where we're gonna fuse inertial navigation, like sensors like IMU, with, for example, GPS. These are usually Kalman-based type of filters, or optimization-based algorithms, like particle filters, Monte Carlo localization, pose graphs, where there we can fuse different types of information. It can come from inertial navigation, but also we can use sensors like laser scanners and cameras. Let's take a look how one example for this type of algorithms. When it comes from filter-based algorithms, here's an example where we have an autonomous boat that we want to estimate the position of this boat. And for this, we're going to use an inertial sensor fusion algorithm called ENS filter to estimate the orientation and position over time. These algorithms, they are optimized for different sensor configurations, output requirement, and motion constraints. So we can use directly fuse different types of sensors. So the IMU, for example, with the GPS, to have an estimation of the position of the boat over time. An important step also when we're using this type of filters is to perform tuning. We have some automatic tuning algorithms that let us tune the filters, the sensor fusion filters, to the specific noise of your sensors. And as I mentioned, the other group of localization algorithms are the optimization-based algorithms. A very classic type of optimization-based algorithm is the Monte Carlo localization, which is based on a particle filter algorithm. So as you can see in the beginning, there are particles all over the map, and we are trying to relocalize this robot inside a known map. In the beginning, you don't know where the robot is, so the particles are quite spread. However, when we start to perform scan matching, the algorithm is going to start to optimize and be able to arrive to the point where it knows the location of it and all the particles are concentrated in the right location. In this case here, we know the map, so we can relocalize inside this map. However, sometimes we don't have even this information of the map. We just have an autonomous system that we want to move in an unknown environment. This is a problem that is quite classic in robotic systems because it's what we call a chicken and egg problem. Because to have a precise localization of a system, we need a precise map of the system. And to have a precise map of the system, we need also the localization. So the two things need to be done simultaneously. How does that work? Given different types of sensor inputs, can be camera image, LiDAR scan, or odometry information, we're going to build a map of an unknown environment while simultaneously keeping track of the robot's pose. Here we're talking about mapping, so just a small parenthesis, there are different ways of keeping maps in MATLAB. A very common one is occupancy grids. It can be 2D or 3D, but the idea of an occupancy grid is that the environment is breaking into cells, and at each cell, we're going to store the information, the probability of the cell being occupied or free. So here it's, for example, 3D maps that were created with laser scanners for automated driving and for drones. We have several examples of SLAM algorithms in the documentation. I separated two. This one is using cameras and the Unreal environment that we saw before. So you already know a little about what is here below. We have the different blocks that let us connect to the Unreal environment, define our vehicle, define the sensor that is connected to it. And as you can see, there is a block that is connected to the camera. This block is what is going to perform this LAM algorithm. And maybe it's too small to see, but the idea of this algorithm is that at each frame, it's going to detect features on it that's going to be added to this map. And these features are going to be tracked over time. The tracking of it is going to make it create an optimization algorithm for the localization, and also keeping them is going to create the map as you see below. And once this vehicle comes back to a position that is already known, in the SLAM algorithm, there is something called loop closure. That is an optimization algorithm that lets you close the loop and actually optimize all the drift error that was accumulated over time. The same idea can be done with laser scanners. So the only difference is that now, instead of tracking the features of the camera over time, we're going to do scan matching. We're going to match laser scans over time to estimate the localization. At the same time, we're creating a map of the environment, as we're seeing here. So this was the last part of the perception. Before I move to the planning and design, is there any questions? No questions?
No
Okay.
question.
So far, just as a recap, what we did, we modelized a robotics system, we connected sensors, we gathered information from the sensors, we perceive the environment, and we know where we are in the environment and what the environment looks like. So what is now to do is to actually plan and decide what to do. There are different types of motion planning algorithms, but the main idea is that we want to find from a point A how to arrive to a point B. If we have a static map that is not going to change, that's called global planning. We're just going to plan from A to B and perform this trajectory. However, sometimes we might need to do what we call local replanning. It means during the trajectory of the autonomous system, an object might show up and we might need to change our trajectory. And there are some different algorithms that can be done to local replanning. For global planning, we have a toolbox. It's called the navigation toolbox that provides multiple path or motion plannings to generate all these sequences, as we can see here in this image, of valid configurations that move an object from a start to a goal end. That is that global planners typically require a map. It can be like the one of occupancy grid map that we see here. And they will check for collisions with the environment and connect and propagate states and use cost functions for finding the optimal path between 2 points. There are different algorithms that we can see here in the list that are developed in MATLAB, from very classic ones, like, for example, the planner I-star that use an I-star type of search in occupancy grid maps, or the planner RRT that it's a type of algorithm that use rapidly exploring random tree planning for solving all the geometric planning problems to find an optimal path. Most of the time, we cannot say like this is one planner is necessarily better than other. We need to understand the application and simulate it to understand which one is the better for our application. So there is a way to benchmark all these path planners. We have an example in the documentation that shows how to benchmark them. In this example, we have this warehouse floor plan. So it's an occupancy grid map and some starting points and goal locations. And we're going to launch different types of algorithms, as we see here. And we're going to use different types of parameters to compare their results. It can be execution time, which is the time taken to plan and execute this path planning. It can be the smoothness, which is how smooth is the path for all the poses creation, for all the movements of the robot. It can be the path length, that is really the size of the path, how long is it. And the clearance, which is how close and the minimum distance to the obstacles in the environment. So there are a big list of parameters that let you compare between them and then find what is the optimal type of path planner for your application. So these are global planners. As a local trajectory planner, this example used FreeNet path. So it demonstrates how to plan a local trajectory in a highway, very dynamic driving scenario where the vehicles are moving between lanes. The idea is that it uses a reference path, so it's the one that we see here in green, and it creates a list of alternative trajectories, the ones in gray, and by using the list of obstacles, it's going to modify the trajectory to an alternative one or not. And it's going to also have a logic to move from just keeping the lane, changing lanes, or vehicle following maneuvers. It's all based on the cost and how it's a collision-free motion or not. So this is an example for automated driving, but I would just like to mention that we also have examples for other types of autonomous systems. It can be drones. For example, here it's an example of a drone that is going to create the trajectory in this very simple cuboid world, but using a type of path planner, that is the exploring random tree path planner, to move from a point A to a point B in a 3D map. So it needs to also consider X, Y, and Z positions. Similarly, we have here an example of a path planning algorithm for robotic arms that needs to move from a point A for a point B to grab an object. So this was just a small introduction and overview of planning algorithms. Now let's move to the control, which is one of the last stages of our workflow. So the planners that we saw before, they're going to generate a set of waypoints for our platform to follow. Now we can feed these waypoints to a controller to get actual actuation commands to our platform, and then use feedback to modify, for example, actuation commands based on the curated state of the platform. There are several algorithms available for controlling. You can even, of course, create your own controller with our tools. I listed here some of the commons like Purpose Suite controller, the Stanley controller, and MPC. The first I would like to go over quickly today is the Purpose Suite controller, which is one of the most classics. The idea of this controller is that you can define what is your desired linear velocity, angular velocity, and look-ahead distance. And by the set of waypoints that were defined by your path planner, you have the controller that will guide the robot along these waypoints. However, if you put, for example, an obstacle in front of this controller, of course, it doesn't take into consideration. It's just trying to follow this path planner using the controller it was defined. One way to actually add some logic, let's say there is an obstacle in this path and we want to stop according to this obstacle or change the trajectory, is to add what we call a supervisory control. And I just would like to show you an example of how you can add this supervisory control. So let's think about a Purpose Suite controller in an entire system. So here we have a model of a vehicle, the path controller, and the visualization. So the path controller is made of not just the Purpose Suite controller, but also what we call a model logic. So the Purpose Suite controller is just a block that is going to take as input the pose of the vehicle, the waypoints, and actually give outputs for linear velocity and angular velocity. And the supervisory logic, the idea is that we can connect this to another tool that is on Simulink that's called Stateflow, which is a state machine that lets us define states in the logic of our system. So let's say we can create a state that is going to follow the trajectory just until a moment that it's going to detect something and it's going to have to stop or recreate the trajectory. This type of state flow is quite commonly used in robotics applications because we often need to create this type of logic between different actions of our autonomous systems. Here is another example of how this type of state flow can be used in an automated driving environment. Here we have an ego car that is moving in a highway. We have a dashboard that lets us see and visualize if there is a lane that is occupied or free. So for example, the left lane here is safe, while the current lane of the ego vehicle is going to be unsafe because the vehicle is getting too close to another. This is going to activate a condition in the state machine that's going to say vehicle now needs to change lane because it's getting too close to another vehicle. And it's going to call, it's going to trigger the change lane action, and the vehicle actually is going to change the lane after it. So this is an example of how this type of state machines can be very useful for autonomous systems. Also, I would like to mention some other examples of control. One that is becoming quite popular today is the MPC, the Model Predictive Control. So once we have used a path planner, one of the ways of following the path, it's using a nonlinear model predictive control to, for example, steer the vehicle for the parking maneuvers. The idea is that the MPC, it's an optimal control technique that it's going to calculate the control actions to minimize a cost function that is going to take into consideration all the constraints of the environment, for example, the obstacles that are in the environment and the constraints of the movement of the vehicle. And it's going to generate as an output, for example, the steering angle and the vehicle velocity to follow the planned path and park the vehicle in this empty space. If you want to know more about model predictive control toolbox, there is a toolbox that provides function, applications, and Simulink models that facilitate this designing and simulation of controllers using linear and nonlinear model predictive control. And as a last example of how to control autonomous systems, I would like to mention reinforcement learning, because many control problems require complex and most of the time nonlinear control architectures. And techniques like MPC can be used and good for solving these problems. However, it requires a domain expertise. You need to really understand about MPC from control engineers. For example, for tuning gains and parameters that are very hard to tune. So one alternative that engineers are exploring nowadays is the use of deep neural networks. So trained using reinforcement learning techniques to implement this complex type of controllers. The idea is that these systems can be self-taught without the intervention of an expert of control system. And they can use different types of information as input, as the sensors, or even just an image of the camera of the vehicle as an input, and the algorithm of reinforcement learning is going to try to estimate an end-to-end controller that's going to generate actions directly from the raw data. So here we go for controlling. Now we arrive to the last part, that is connect and deploy. In the connection part, I will present to you how we can connect to ROS. I don't know if everyone here is familiar with ROS. So ROS, it's first of all means robot operating system, but it's not really an operating system. It's more like a middleware. And it's really a framework that is quite commonly used by the robotics community. The idea is that it brings together different elements like the robot development ecosystem, development tools and capabilities. As its core, it's an infrastructure that it's an architecture for distributed inter-process communication. So you have different nodes that's going to communicate between them to perform different tasks of a robotic system. For example, you can have a node that is going to be performing the controller of the robot, another one for perception, another one for path planning, and they're going to communicate between each other using this framework that changes messages, and you can receive them through the different nodes and communicate them between them. It's a multi-language interface. You can use C++, Python, Lua, Java, and there is also a way to interact with it using MATLAB. And that's what I'm going to show here today. And also as an information, there is ROS and ROS2. I will not go into details of the difference between the two of them. It's the two different versions that have some different characteristics, but the idea is that it's quite similar how MATLAB and Simulink interacts to both of them. So let's see how this interaction works. So on the right, we have a typical ROS system that usually turns in a Linux machine, where you have different ROS nodes doing different types of processing and different types of applications that is connected to our simulator or to the real hardware. And in the left, we have a MATLAB Simulink environment that can be used for modeling the system and performing all the things we have been looking so far today: perception, planning, and decision and control. And how can we communicate between these two different systems? The first way is in the offline analysis. So we can use the data sets that are created from the ROS environments. They are called ROSbag. So basically, if a ROS machine is it's publishing several messages, we can gather all these messages in a file that's called ROSbag. This is a native ROS type of file, and load them into the MATLAB Simulink Word frameworks to analyze this data and then plugging into different types of algorithms. Here's an example of how this can be done. For example, it can be done through MATLAB, or we can just call the function called ROSbag with the name of the bag, select one of the topics that is in this bag, read the message and visualize it, or through a Simulink block where we can get the topic from the Simulink block and also visualize it. This type of offline analysis is quite useful if you just have a robot and want to do a test out of the loop. You get all the messages and try different types of algorithms with the message that were exchanged inside this robot or inside the simulation. In this case here, it was a simulation. We just gathered all the messages that were published in a simulation. Using MATLAB, we can also write our own ROSbag files if we want to exchange information between a system that use ROSbag files. So we can, for example, compress ROS messages take ROS message, change the values on it, and then write it in a new ROSbag file. This is the workflow for offline analysis. Another way to communicate to them is through the phase of prototyping, which is a directly connection between the MATLAB Simulink environment and the ROS environment. What does that mean? It means that it's really the ROS network and our machine turning with MATLAB and Simulink can communicate between each other. Here is an example where we have a machine turning a simulator, but it could also be directly a robot in the ROS environment. And using the commands here in MATLAB, we can, for example, use a command called ROS topic list to visualize all the topics that are published by ROS. We can publish a position of the joint and move the robot, or just receive, for example, one of the data from their sensors, for example, the image here, using a subscriber. The same thing can be done using Simulink, of course. There are ways to connect directly Gazebo and Simulink. So here we are connecting Gazebo by taking the information from the sensors that are turning here in Gazebo. So it means the cameras that we are seeing this image. We're going to perform some image processing, deep learning algorithm to detect where the robot should turn. And then we're going to send this command back to Gazebo. So the idea is that we can gather the information, process them, and then send the command back to Gazebo and see the result live on the ROS machine. So this is the phase of prototyping, where we can test simultaneously algorithms developed in MATLAB with the ROS environment. And the last phase, it's what we call deployment, is the ROS node generation, where we're going to generate C++ code that's going to be independent of MATLAB and that can be deployed to the ROS environment to turn directly on the ROS machine or in the robot. Here is a small example for this. We have developed a controller of a robot in Simulink, and want to deploy this directly to the robot. For this, we can use an app that facilitates this deployment, the robot operating system app. We choose what type of ROS system we want to deploy. Then we can connect to the robot. By this, we just need to set up the IP of the machine, the username, and the folder we want to deploy. And after defining these parameters, we can also test the connection with the robot. So in this, we can see that we can ping the robot and establish directly a connection between Simulink and the machine with ROS. And in the end, we can build the model or build and load directly the model on the robot, or build and even launch this model on the robot. This then is going to generate a C++ code that is going to be deployed directly on the robot. And this code is independent of MATLAB. It means you don't need a MATLAB license in the robot to run it. And to finalize our workflow, talking here about deployment with ROS, I just also would like to mention that deployment can be in several formats. We can deploy for embedded targets in C, C++. We can for FPGAs in the VHDL, Verilog, and even we can generate CUDA code for NVIDIA graphic cards. The idea is that all our methods, their algorithms that are developed in all the phases that we've been seeing here, from modeling until control, we can then deploy to our platforms quite in a straight way using what we call coder products. So these are toolboxes that are going to transform our Simulink MATLAB code into other languages. I will not go into details of this phase, but there are a lot of documentation about how to generate this code to different types of targets. Here I separated some of the classic methods that we presented so far. So perception algorithms like line detection, control, path planning, where the models in Simulink were transformed to C++ code for then be used in embedded hardware. So now we finalized our workflow. A lot was mentioned during this presentation. There are a lot of tools that connect all these different development of MATLAB and Simulink for autonomous robotic systems. As you probably noticed throughout this presentation, there are several toolboxes that help different parts of the system. The idea is, depending where you are, there is probably a toolbox specialized on it that can facilitate your job with already functions that going to make it much easier. So since the modelization of the platform with Simscape until the development of algorithm with all the deep learning, computer vision, state flow, navigation toolboxes, with the connection to the whole ROS, with the ROS toolboxes, and in the end, the deployment with all the coder products where we can generate codes. This type of tools, they are used in the industry. I also select some user cases that are interested in using autonomous systems with our tools. I'll not go into details of them. I will let you take a look in their user stories later, but a very interesting one, for example, is the German Aerospace Center that developed all the blocks that we mentioned so far. So perception, path planning, calibration, control with MATLAB and Simulinks for this robot called Justin, this humanoid robot that we see here in the middle. I also separated several resources that can help you get started with all that was presented here today. I hope you find something similar to what you're working on. The good news is that we have a lot of technical content to get started with anything particular that you're looking for. I separated the toolboxes that were the most mentioned here during this presentation, and there are a lot of specific tools for automated systems, and also some tutorials that shows you all the steps of the different stages that I talked here in this presentation. So thank you everyone for your attention, and let me know if you have any questions.